Hello and welcome back. Alright, in this video we are going to be taking a look at solving the shortest path problem with our graph that we've been building up. The shortest path problem is what is the shortest path of vertices between one node and another node. So we're going to go ahead and take a look at how we solve that. Now, this is actually already a well-defined problem. There's already a solution to it, and since you may have been exposed to this solution if you've gone through any computer science or software engineering courses at a university or a college, maybe even in high school classes, or you may have been exposed to it from a friend telling you, oh yeah, there's this algorithm that does this for you. Regardless of how you were exposed to it, or if you don't even know if it's exposed, it sounds like a problem that's been well defined. And when that's the case, we should try to leverage algorithms that people have already come up with whenever possible. We don't want to spend all of our time re-implementing, or not necessarily re-implementing, but coming up with algorithms for complex tasks when that answer has already been provided for us. As software engineers, we should really leverage the brilliance or the genius of other people and make use of their solutions when it's possible. So, how do we go about finding out about this shortest path algorithm? Well, jump over to your favorite browser and open up your favorite search engine, and we type in shortest path algorithm. This first link looks pretty good. Some sort of algorithm that's Dijkstra's, if you don't know what that is, but let's go ahead and follow this link and see what we get. Alright, so we get a Wikipedia article entry for Dijkstra's algorithm, conceived by Dutch computer scientist, blah blah blah, solves a single source shortest path problem for a graph. That sounds exactly like what we're looking for. Alright, so if we look down here in the contents, we can see, oh, here's a description of the algorithm. Perfect. I'm going to need to know this to understand the algorithm and how it works, but there's also this great little pseudocode link. And this is another thing, as software engineers, we need to be able to take someone's pseudocode, either pseudocode that we've come up with ourselves and whiteboarded out for an approach to a problem, or pseudocode that maybe we've worked with someone else or someone else is giving us on how to solve a problem, how to take that code and adapt it to our specific problem. Now, this is a great general overview of the code that we're going to be needing to write to solve this problem, but we're going to have to adapt this to using our data structures, our graphs, and our requirements. If we look through here, for example, I told you I wanted to find the shortest path between two nodes. Well, we look at this function. It says, hey, it takes in a graph. It also takes in a source, but it doesn't take in the target node. And that's because Dijkstra's algorithm is really about finding the shortest path, the path distances from all nodes to your source node. So we're gonna optimize this implementation so that it actually returns just the piece of data we want. It doesn't do a lot of extra work that we don't actually need. Okay, so the first thing we want to do is let's go ahead and jump over into the whiteboard and talk about this algorithm and what it's going to look like, and actually how it works. Okay, so I've actually copied and pasted that pseudocode in here so that we can refer to it without having to flip back and forth. And I've also drawn our graph that we had from the code that we wrote in our last video. Now, I did make one modification. There was a edge that we added between B to D that used to be weight 6. And as I was looking through that, I'm like, oh, you know what? That's actually going to give us two of the same answers, or two possible answers, if we ask the question, what's the shortest path between A to D? So to make it so that there's not an ambiguous answer, or not really ambiguous, but that there are two different answers, I changed the pathway between B to D. Because the question that we're going to be asking is, what is the shortest path between A to D? And if I left this originally as 6 as it was, then we could have gone to A to B to D, and that would have given us 7. And then A to B, B to C, C to D would have given us 7 as well, 4 plus 2 plus 3. So I actually only want there to be one answer. Okay, so that was the update that we made to the code. Okay, so let's go ahead and take a look at this algorithm. And first off, we note that, hey, we're going to have to actually change this. We're going to need to add a target in here. Okay, but that's not too big a deal. Let's look at let's look at a high level first of I'll kind of walk through the code and what it's doing, and then we'll go through and actually focus on some of the actual intricacies of those things. So if we look at lines 2 through 4 right here, essentially what we're doing is we're setting up some initializations. We're going to have these two variables, dist and previous, which are actually, when you see pseudocode like this is actually being represented as a hash table or a map. So we'll call it a hash, a map, could also be called a dictionary. It's a data structure that takes a key value, this v, and associates a value with that key. So if you can think of it like an index in a book, where if you look up the word, let's say it's a programming book, and you look up the word for, well, for, you go into the index, you find for, and then it has a bunch of page numbers that are associated with that value, with that key, that for key. That's exactly what this hash table is. It's just a way to associate a bunch of data with a simple item that we have that we can always look it up with. All right, so previous is going to be the same thing. It's going to be another hash table. And then we have this distance. We're going to set the source to 0. So basically all that's doing is saying, hey, from the node that I'm on, it doesn't take any effort to get back to myself. Okay, that seems reasonable enough. Q is going to be the set of all nodes in a graph. So you can see that's kind of a sentence that actually doesn't even look like code at all. So we're going to have to figure out what that actually means in our implementation. But Q is just this initial set of all of the nodes in our graph. So we have A, B, C, and D. That will be what's in Q initially. And then the idea of the algorithm is just to go ahead and loop through all of those nodes and figure out what the distances are between there. And as we visited a node, we go ahead and get rid of them. And then we traverse all of the edges, and eventually we'll get back to the node that we want to do. All right, so let's go ahead and walk through an example of what's going on here, just so we can kind of get a little bit better idea of how the algorithm actually works. So I'm going to create a table over here that is going to represent our distance and previous variables. So we'll have dist right here, and we'll have previous right here, and they're going to share the same key value because you'll notice that this for loop is for every vertex v in the graph. So for every node that's in this graph, we're going to basically associate some value with that. So let's go ahead and draw what this table kind of looks like. So we have A here, we have B, we have C, and we have D. And so in the beginning, the distance is set to infinity for all of those, and then undefined for the previous. Okay, perfect. All right, so we're starting at source. So distance, we said our problem is going to be finding the shortest path between A. So this very first, our line 5 right here, this real first part of our code is going to update our distance dictionary, or our distance map. The value for A is going to now become 0. Okay, so let's go ahead and erase that. And that's now 0. And draw a line through it to make it more clear. Okay, so that's 0. Now Q, we'll draw what Q is down here. Q is going to be a set. And there's actually a standard type for that. It's called set. And up here, the C++ one for our dictionary is called a map. All right. Okay, so Q is initially set to A, B, C, and D. Okay, so let's just do that. A, B, C, and D. Okay, so now this asks the question, or this poses a loop here that says, hey, while we still have nodes to visit, let's go ahead and do some work. So in line 7, Q obviously is not empty, so we're going to continue on. So now we have this temporary variable U. And this U is just a node that we're going to be looking at. And so the vertex in Q with the smallest distance. Okay. So what we're going to do is the first time through here, so the smallest distance in our list here. So if we look at our current list, we have the values 0, infinity, infinity, infinity. So what value is the smallest? The smallest value is indeed 0. So in the beginning, U gets set to A. So let's just do that. So we'll do first time through U equals the A node. Okay, and so now if our distance to U is infinity, then we're going to break out. And so what this is saying is, you know what, we can't get to anywhere from here, so we're just going to break. So this, in this case, is not true for us. Distance of A, for node A, is 0. So we're going to continue on. What we are going to do, though, is we're going to remove U from the source. Okay? So U is no longer going to be in Q. I'm sorry, we're going to remove U from Q, not U from source. So Q no longer has A in it. And now what we want to do is we want to traverse all of the edges inside our graph that come off of A. So this is where that adjacency list is that we implemented in our graph implementation is going to come into use. If we had used our original implementation of the graph, remember, getting those edges would have actually been a non-trivial thing to do. It would have taken up time, and we wouldn't have actually already had that data there. Okay, so for each neighbor V of U, go ahead and do some work. So what we're going to do is we're going to set alt. Okay. Well, so the first thing is let's just pick an edge. So let's say this V is going to equal the edge between A to B. So let's just write it as that. And then, so alt is going to be the distance of U, which is 0, plus the distance between U and V. And so that's the distance between A and B, which is the weight of our edge. And so that's going to be 1. So alt equals 1. Okay. So now we need to ask the question, hey, based on our distances that we've actually kept track, is the path to get to A cheaper going through this node, or is it cheaper going through a previous node? So that's our question. If alt, so we have if 1 is less than distance of V, and so V in this case is our node B, and so we look up B and we have infinity. So obviously 1 is less than infinity. So now we update distance of V to alt. Okay. So let's go ahead and get rid of this. Distance for V is 1. Okay. And now we ask then we also set previous of V is U. So what's that node that we're going to get back to? This previous table is going to be used so that we can traverse our path back to our source. All right, so from B, that is going to be node U. So U was A, so our previous node here is A. All right, and now what do? We have another edge. We have this A to D edge. So let's go ahead and run through what happens in here. So V is going to be our A to D edge. So really V is this D node right here. So alt equals the distance of U. So again, that's 0 because that's the distance at A. And now the distance of U right here, or sorry, the distance between U and V is 10. Okay? So our alt equals 10. 0 plus 10 is 10. All right, so now we ask the question, is the alt, so if 10 is less than our distance to V. And now V is D, so D is going to say, yeah, you know what, infinity is less than that, so that's going to be 10. Okay? And previous is going to be set to A. Wonderful. All right, so that is our first iteration through this entire list. Now what we want to do is go ahead and I'm gonna delete this piece right here, and we're going to look at what happens when B is now used. All right, because right we do while Q is not empty. Let's go ahead and find the smallest distance. All right, so we're back up at the top. So the smallest distance that we have in here. So U is the vertex in Q with the smallest distance. So we're actually only looking at the vertex in Q. So we're only looking at B, C, and D. So between B, C, and D, the only what's the smallest node? And so we have the options of 1, infinity, or 10. Well, you know what? Obviously 1 is going to be the smallest distance. So that means our U is going to be our B node. Okay, so now the distance is not infinity at B. We're going to go ahead and remove B from the list now because B is being used currently. And now we're going to fill in the table, just like we did before, between all of our edges. So let's just grab the first one. We'll say that the first one we're going to be looking at is C. So V is going to be the C node right here. So we're going to get our edge from B to C. Okay, our alt is going to equal our distance of U. So U is B this time. So we're going to have 1 plus this edge weight, which is 2. All right, so our alt is 3. All right, so now we ask the question, is 3 less than our distance to V? So V is C, V is infinity. Well, yes, it is. 3 is less than infinity. So now we're going to update our tables. We're going to update our C table. Our distance just there is going to be 3. And our previous node is going to be set to B. Perfect. All right. So we've done this edge. Now we need to do this edge. So now V. So this is our loop. So now we have another iteration for our edge loop. So V is going to be D. Now the distance, so alt equals our distance of U. Our U is currently set to B, so B is 1, plus this edge weight. And this edge weight is 5. So our total here is 6. Okay, so now we ask the question, if 6 less than our distance to V. Now, remember that V is D, okay? So what we look up in our table, we see D is not infinity. And so what this means that if whenever you look at this table over here for distance, if D is never, or if the distance at your value does not equal infinity, that means there was actually a way to get to that node. And so this is where the meat of this algorithm is really going to happen here. We're going to say, hey, is 6 less than 10? Why, yes it is. Okay, so that means from the node D, we don't actually want to go to this previous node A. What we really want to do is we want to go to B, because B is the cheaper route to A. All right, so that means we need to update our distances. So our distance goes away. Our distance is no longer 6. Our distance is no longer 10. It is now 6. And our previous node is now B. Perfect. Okay, so we have 2 more iterations to make because we have 2 more items left in our set. Okay, so now we're going to pick the C node. Now you could have started with these nodes in any direction. It doesn't matter. The point is just that you have to traverse all of the items. Okay, so C. So what we got here, we got U is the vertex in here. So now our choices are C and D. Okay, so now we find the smallest one in here, And that's going to be 3 now because the only options we have are C and D. So 3 is less than 6. So that means our U node right here is going to be C. Okay, C, the distance is an infinity. Perfect. All right, so now we're going to use C. So let's go ahead and get rid of it from our set. And now we do all of our edges. This only has one edge. So V is going to be D, which is representing our C to D edge. And so now then we calculate what this alt is. This alt is distance of U. So remember, U is C, so we have 3 as that value, plus our distance between U and V. And that edge weight here is 4. Okay, so alt equals 7. So now we ask the question, is 7 less than the distance at V? And remember, V is D, so we get the distance value of 6. And you say, you know what? It's not. 7 is not less than 6. So we're not going to update our table because the path to go from A to B to C to D is actually more expensive than the path that we've already calculated from D to B to A. Okay, so now what we do is there's no other edges, so our table iteration for this one is done. Okay, and so now we're left with Q is not empty, so U is going to be the smallest value in our set Q. Well, we only have one value, so that means it's got to be D. All right, so our distance, not infinity. Okay, now we remove D because now we're going to be looking at it. Okay. Oh, I'm sorry. There actually was another edge from C. It went to B. But since B has already been visited, we don't look at it. Okay, so U to D. U to D. I'm sorry, I lost my train of thought. Okay, so our distance is not infinity. We removed U from Q for each neighbor of V of U. And see, so notice this caveat right here, where V has not yet been removed from Q. So what this is saying is for every neighbor of V in U that doesn't exist in Q, that does exist in Q, then go ahead and do our search. Okay, so now we get alt, distance of U. So the distance for U, so U is D, alt is going to be 6, plus the distance between U and V. Well, so actually, our caveat right here is we never get into this loop. Sorry. I just explained that, and then I continue on working. So if we look at D, for each neighbor of V in U, right? So U, if it doesn't actually exist in here from Q, D is done. We don't actually have to look at any of these edges because there are no neighbors here that these nodes actually exist in Q. So at this point, we've actually created our table that tells you the shortest paths from all of the nodes back to A. So how do we actually find out our answer? Well, depending on our node, we just ask that node, and we're good to go. So if we wanted the shortest path from B, well, we know the answer. We look up B. Okay, so obviously we start at B, and then we go to the previous, which is A, and we're done because A doesn't have a previous, right? A is the actual source that we're looking for. If we wanted to know the shortest path from C, well, obviously we have C. So we look up C, the previous is B, and then we go to A. Perfect. For D, what we do is we have D. Okay, so we look up D, the previous is B, and then we go to A. So this is indeed the shortest path at the cost of 6. If we go D to B, that costs 5, B to A is 6. So that was the quick high-level, well, I guess we kind of went a little bit low-level, introduction to Dijkstra's algorithm. I don't expect you to understand or completely get this algorithm from this quick walkthrough. What you should do, though, is come up with some more examples. Walk through these steps and just keep practicing that until you actually understand that. And then in the next video, we'll go ahead and go through the implementation of this in C++ so that we can actually figure out how we turn that pseudocode into real code. And then I'll also briefly touch on those STL types that we're going to be looking at. All right, thanks.